Welcome everybody. So today we have Maria Ramos here with us in person. We still have a few places, so if you would like to watch the seminar in person, then you're welcome here in Sala de Juntas. So she is visiting IGFAE, and today she will give us a seminar about multi-muon signatures of composite Higgs models. Please, Maria.
Hi, so thanks a lot for having me. Today I will be exploring these signatures, but I decided to spend some minutes giving a broader motivation for these models, and also mention the basic ideas upon which they are constructed, and then I will focus on this signature in particular. So I would like to start with this broad question about where is new physics likely to appear? And it's useful to consider the standard model effective field theory approach to address this question, which is getting more and more popular given that we have found no direct evidence of new physics. So here we really have the broadest and the most unbiased view of new physics, because we don't have to decide upon a particular model in the UV. We just assume a separation of scales such that these hypothetical heavy resonances can be integrated out and its effects can be parameterized by these higher dimensional operators. Also, yes, here. So what this basically means is that we construct all allowed operators by symmetries, which can be made of the standard model degrees of freedom. So what happens here is that already at dimension 5, we have this Weinberg operator, which can generate neutrino masses for new physics scales of around 10 to 15 GeV. And then if you go on and go to dimension 6, so here this lambda is the cutoff of the new physics scale, then we find that we have, for instance, these 4 fermion operators, which can violate barrier number and allow proton to decay. And we also have an explanation for why this should be suppressed, because it goes with 1 more power of the new physics scale. And it gets even more interesting if you take bosonic interactions. So here the phi denotes the Higgs boson, because then you can change the nature of the electroweak phase transition and can, for instance, have one of the conditions to explain baryogenesis, which we don't find in the standard model alone. So this picture looks actually very promising. Furthermore, because these 10 to 15 GeV is still compatible with a bounce from proton decay. So this would really make us suspicious about the fact that new physics could be very, very far from us. And the glaring problem that changes this picture is actually found in the standard model itself when you look into the Higgs sectors. So here we find in our theory a good parameterization. Why is this blue? Sorry.
I think it's selected somehow.
Okay. So
yeah.
Okay, sorry. So here, when you take into account our Higgs theory, we have a good parameterization of electroweak symmetry breaking by having this scalar, the Higgs, which here it's denoted by phi, that gains a vacuum expectation value. However, to get this kind of parameterization, we have to introduce here the Higgs mass. So this is a quadratic term, which we expected to go as large as our largest cutoff in the theory. So this lambda I was presenting you before. And here, the fact that we find a huge discrepancy between this very large scale and the Higgs mass, it's really the essence of the hierarchy problem. And if you want to go into a more technical language, this basically would come from any heavy physics that would couple to the Higgs boson, which is very likely to be the case if you consider our popular frameworks to address neutrino masses or even dark matter. So when you integrate this particle out, you see that the Higgs mass receives huge corrections, which go with the mass of this particle, this heavy particle itself. And this gives us a physical meaning to this lambda, this cutoff scale I was telling you about. So this is the essence of the hierarchy problem, that we don't find any mechanism to protect the Higgs mass. And before addressing the composite solution, I also wanted to tell you about some fresh perspective on this problem, because the fact is that we have found no evidence of new physics since the Higgs discovery, so for now, more or less 10 years. And this problem lies basically on our search for natural theories. So this naive expectation that we should have order 1 parameters in our theory, because if they are very small, then we would expect some new underlying phenomena to appear. And this is really a very useful principle that was behind many discoveries like the charm quark or the meson. But some people have argued that by now we should really accept the Higgs mass as just an input parameter because we really don't know the UV and we have found nothing so far. But I would like to argue that this is not such an interesting approach because although naturalness is not really a fundamental principle, it's very useful to find simpler theories from which, for instance, the Higgs mass could come as an output. Otherwise, we would just give up on the problem. And it's also worth noting that our best solutions that target this hierarchy problem are usually the ones who have the most compelling candidates for other issues too, such as dark matter. So I think a more interesting question is to ask if our best theories are as motivated now as they were before, and they can solve this problem in a viable and vast region of their parameter space and not just in a single point. And in the composite case, this is really true because what you notice that, I guess, a bit unlike Susie, is that only really the minimal model has been explored a lot. And once you drop this requirement of minimality, you do find many more interesting frameworks and more common frameworks, which can first evade very easily the bounds we have. They can still produce a very natural Higgs mass. And furthermore, they point towards new regions of signal, which were not yet explored. So how do these models really solve the problem? So they are based on one trick of nature we already know it has, which is this ability of producing composite pseudo-boson particles, because this we have observed in QCD already at smaller energies. So what these models do propose is to mimic this QCD sector at higher energies. So they propose a new strongly interacting sector that confines near the TV at this F scale, and from which the Higgs is produced as a composite particle. So above this cutoff, basically, we no longer have a Higgs to suffer from the problem because we would only be seeing its constituents, such as the case of the proton and the quarks. Furthermore, we still have to explain how can we generate this hierarchy from the cutoff near the TV to the Higgs mass at the electric scale. And this can come assuming that the global symmetry of the strong sector is spontaneously broken. Again, in analogy, what we have seen in QCD for the case of the pion. And in the process of breaking this symmetry spontaneously, you will produce Goldstone bosons. So we can understand that the Higgs is lighter than this new physics scale by two reasons. First, its mass is generated radiatively, so it's 4 pi suppressed. Well, the square should be outside. And then because it comes proportional to this small parameter that in the limit that goes to 0, we recover a symmetry. So to recover this limit, we expect all the effects to the Higgs mass to come proportional to this parameter itself. So this is what makes us understand that it can be still natural and light. And so what are really the realistic configurations for these models? So we do have a new physics scale. So we expect all sorts of resonance to lie nearby, which can be new vectors or new vector-like fermions. So here I use the L for a vector-like lepton and Q for quark. And we expect the second lighter set of Goldstone particles, which in the limit, the symmetry of the strong group is exact, then they would be exactly massless. So we do have to find a way and assume a way for the composite Higgs here to communicate with the standard model. More or less, we have to, furthermore, we have to generate the Yukawa couplings of the Higgs to the standard model fermions. And by assumption, we say that this linear interaction between the light fermions of the standard model and the heavy composite fermions is what explicitly break the symmetry and generates all the symmetry breaking effects. So this is the assumption, and this can give a mass to this set of Goldstone particles, and they become pseudo-Goldstones. So when you really take into account what is the common setup in which you have an extended symmetry in the global sector, you will see that you can naturally produce many more pseudo-Goldstone bosons than just the Higgs. And this is the kind of realistic phenomenology I wanted to talk about. So given this setup of non-minimal models, what are really the most compelling candidates we can consider to start, because we cannot probe all these symmetries at once. And here I will argue that one of the most compelling particles here are these heavy vector and light scalars, which are singlets of the standard model Higgs group. So let me start with the case of the vectors. Why do we care about them in this context? So the big motivation here comes from the B anomalies, because they really provide the largest coherent set of deviations we have so far beyond the standard model physics. And here I'm focusing on the lepton flavor universality ratios. So these ratios of RK and RK star and RD, the first of which probe a flavor changing neutral current of a B quark to a strange. And basically what we are seeing is that if there is new physics, it should couple more to the muons than to the lighter generations of leptons. In the RD case, we are probing a flavor changing charge current of a B quark into a charm, and we are seeing a preferential couple to taus than to the lighter generations. But here I will focus only on this RK star, also because it's a robust measurement now, given the last result from the LHCb, which alone measuring this observable found a deviation of around 3 sigmas regarding the standard model prediction. So the next step that people have been worked on is trying to see, so doing a model independent approach, including all effective operators to see what is the one which better fits, or the ones which better fit the data. And they found that this is the case of these kind of semi-leptonic operators involving left-handed currents. And if you take this anomaly RK alone, what we really need is a small coupling to third generation quarks, and small because this kind of flavor changing neutral process occur in the standard model at the loop level. So if we want to be, to give a larger, an enhancement to that, we don't need a very sizable effect. So here, like I said, we need to have a preferential coupling to third generation quarks, and then a preferential coupling to muons, basically, taking these RK anomalies alone. So what could then be behind this kind of effective operator? And the most compelling candidates right now are a Z prime and a lepton quark. I will focus on the case of a Z prime. So here you have a plot showing the coupling to an S and a B quark, which would come after introducing the C kappa M factors from this coupling here, versus the mass of Z prime, which can explain these RK anomalies. So here in the solid black line, this could be explained at the 1 sigma level. And superimpose our bounds from meson mixing, this delta MS, because this C prime would actually contribute at 3 level, this kind of B oscillating system. So there are important bounds there. And in this work, I will focus on the bounds of 2015, basically because the most recent ones predicted here in this reference, to the best of my knowledge, still lack some confirmation. So moving on, we still have to worry about direct searches on this Z prime. And there are some examples in which of the LHC searches, considering the on-shell production of this vector that then can decay into muons. So this reference here recasted some atlas search and found this limit in red. And here superimposed, you have this dashed black line, which is the production cross-section, assuming that this decay into muons is the only decay mode of these vector particles. So you see here that this analysis could probe masses of around 2 TeV. However, indeed, like I told you in the beginning, if you consider realistic frameworks, so you don't consider the Z prime alone, but really an embedding from which it can emerge, such as the composite one, then you will naturally find other decay modes for this particle. Because like I told you, there are more particles in the composite vector to which the V can decay to, namely these heavy composite fermions. And because they couple through a strong coupling, this decay mode will actually dominate very easily. So in this case, you open this. Sorry?
Is there a question? No.
Okay, but if you open this decay mode of a V into a vector like lepton and a muon, then you open this new decay mode in blue. And of course, the other one gets more suppressed because it's penalized by the smaller branching ratio. And in this case, your limit gets very weaker. So it goes to around 1.2 TeV in mass. So indeed, these Z primes still make a compelling candidate to solve these anomalies. So the other case would be why we want to consider two light scalars. And the case of in which they are singlets of the standard model gauge group is actually very common. So in many extended symmetries, you are producing these kind of particles. Furthermore, of course, these kind of light pseudoscalars can also be a candidate for a strong CP problem. They can play the role of the axion. They are also very important in cases of dark sectors, because if you consider opening new annihilation channels for dark matter, so if you have lighter particles, then you can more easily evade the bounds. And in this case, WIMPs can be still very alive if, for instance, this mediator is coupling more to the muons, in which case this scenario presents the weakest bounds from direct detection, which is really when you try to probe the stable products that come from dark matter annihilation, which are collected, for instance, in Fermi telescopes. And they also suppress, in case of CP-odd scalars, the dark matter annihilation with the nucleus, because they can make it happen only at the loop level. These kind of muon-philic scenarios are also very important to accommodate other anomalies, such as the case of the G-2, because they can contribute at the loop level to the effective interaction between the photon and the muons, for, of course, specific relations between the coupling and the mass. So altogether, this motivates us to consider the coupling between this vector and these light muon-philic particles. And note here that we are assuming a very large separation of scales, which is actually hard to accommodate in other models which are not composite. And like I told you, motivated by the anomalies, we assume preferential coupling of this vector to the third generation. And in the case of composite setups, these kind of muon-philic scenarios can appear very easily too. They depend on the quantum numbers of these vector-like fermions, which give the source of the symmetry breaking. So if the quarks respect this shift symmetry of the scalars, you naturally have these kind of leptophilic scenarios. And if you want to take a more detailed look into what these models give you, so by assumption, like I told you, these particles of composite sector, these scalars cannot communicate directly with the standard model. So they have to communicate through these heavy composite fermions. So the Higgs itself communicates with the standard model in the same way. And therefore you have the fact that these mixing angles will be a function of the Yukawa couplings. And that's why in these leptophilic scenarios, the Yukawa interactions and the couplings of these new particles are suppressed by the Yukawa of the muon or even lighter leptons. And if you take a look into this picture, now you can just close the loop here and you also generate masses. And in particular, they go again with the mixing angles, which are functions of the Yukawa couplings. So you will naturally have masses of the order of the GeV or below in these scenarios. Furthermore, I also consider the models which give you this kind of trilinear coupling, which can come if you assume that this A2 is, for instance, a scalar and this A1 is a pseudoscalar and CP is preserved in the scalar sector. So this is the kind of setup we want to probe. I don't know if there is any question regarding the model framework itself, or if I can continue.
I have one.
Yeah.
So, but this is probably very naive from a experimental, but I will ask anyway. So, because like usually when you have like composite particles, like you were saying, mesons, for example, the masses of the components are smaller than the mass of the actual produced particle. Like if you take, for instance, a pion, like the mass of the quark U and the quark B is lighter than the mass of the pion. Actually, then you have, it's not an actual sum because there are like the bound, like energy bound corrections. Like for example, when you take an atom, the masses of the, or a nucleus, the masses of the mass of the nucleus is smaller than the sum of the masses of the protons and the neutrons. But here I'm slightly confused in the sense that, like, I would assume that like your whatever composites the Higgs, for example, is at the DeV scale, because this is what you were saying. But then the mass of the Higgs happens to be 100 GeV.
So we basically ignore what these technique fermions that constitute these composite particles are. Although there are some works to study what they could be. And for instance, non-minimal models are also important because they are the ones which can be UV completed at 4 dimensions.
So it's somehow effective, right?
Yeah, exactly. It's completely effective. But regarding the question of the mass of these fermions that, these fermions here that I mentioned are not the ones that really constitute the Higgs boson, because they are constituted by, all these particles are constituted by technique fermions themselves.
Yeah,
so,
that I was understanding, but I was,
but you're basically asking what is the thing that would allow these technique fermions to be even heavier than this particle, right?
Yeah,
yeah.
Like if you have something that composites at the same time, these light particles and these heavy particles, what can it be, right? I mean, because from the standpoint point of view, that you end what, right?
I know that there are some realizations, but I can't, in which they can get that, but I don't know, because this is really an effective approach. So the composite nature is not really important for us, just to solve the hierarchy problem itself. And there's another deviation from QCD, because usually in these models, what you assume is that these vector-like particles should be closer to the Higgs than the vectors, but in QCD, you somehow see the other hierarchy happening too. So there are some differences, which I guess are being worked out in some UV completions. Yeah, so going to experimental signatures. So this is the coupling we want to probe again between the vector and the A particles. And we assume the minimal setup in which we only produce 2 of them. And since this V is so massive, we can integrate it out, and this gives rise to bottom meson decays into the 2 A particles. So like I told you, they have Yukawa couplings, so they can each decay into a pair of muons, which lead to this final state with 4 muons, which was already probed by the LHCb at 8 TeV. Finding this limit of around 10 to minus 9 with 3 femtobarns of data. So what we try to argue in this work is that there are actually compelling reasons to search for alternative decays. One of the main ones is that you have this trilinear interaction between the scalars. So the scalar decay width can easily dominate over the leptonic one. So this triggers instead of 4 muons in the final state, 6. Because this A2 can decay into 2 A1s, and each of them decays into a pair of muons. And to show you how this is very likely, let me just plug in here the expressions. And this basically comes from the fact that in these generic setups, you expect the coupling of the scalars to the fermions to be bounded by this Yukawa coupling, while here in the scalar case, you have a mass in this trilinear coupling, which is by power counting expected to be as large as any other mass in the theory. So naturally, this surpasses this partially decay width into leptons. Furthermore, in the case in which A2 cannot decay into A1s, so its mass is below the 2 masses of this light particle, then we can have instead a 3-body decay of the A2 into 1 A1 and the 2 muons. And here we have to adjust more carefully the parameters because we have a phase space suppression. So basically we have to require that this coupling, this free parameter of the coupling of the A1 to muons is larger than the one of A2 to muons. So we can assume, for instance, that the first is order 1 while the other is orders of magnitude suppressed. And we choose these couplings to have lifetimes below 10 femtoseconds. So these particles will look to have prompt decays at the LHCb. So their flight distance won't be measurable. But of course, the departures from this assumption are also interesting and very plausible. So right now, I'm studying departures from this assumption together with Xavier and Titus, actually. So moving on here, we do have another important motivation to expect alternative decays, which is the fact that the 2-body decay width of the bottom 0 into these scalars goes with the mass splitting between them. So in the case in which they are degenerate in mass, it goes to 0. So in this case, we don't really have a way to prove the model. unless we tag an extra meson, in this case a kaon. And in this case, we expect this kind of final states involving a meson and 6 muons, which were not yet proved experimentally either. So if you want to take a more deeper reason about why this happens, you can regard in these limits, these two particles, A1 and A2, as the real and imaginary components of a complex scalar. And the way it couples to this vector current, to this vector, is via really the nether current in QED, which I denote here by this J mu. And the way to have an interaction with this effective scalar, the B, you have to plug in a derivative. So then you can just integrate by parts to move the derivative around, and then you have the divergence of another current which goes to 0. And that's why you cannot prove these signatures in this limit. So here in the next slide, I'm just showing you how large this ratio can be. So in the plane of the masses. So you see, of course, that along this degenerate line, indeed the two-body decay width goes to 0. However, what I aim to show here is that even for mass splittings of the order 1 GeV or so, the three-body decay width starts becoming important. Here in gray is the region which we theoretically forbid, because basically you're just choosing the mass hierarchy on the other way around, assuming that your A2 particle would be the lightest. And so this would just lead to a redundant phenomenology. So it's also worth pointing out that in the case of 4 muons, if you have a minimal model in which instead of 2 scalars, you just have 1, so they can only go to muons, this case of 4 muons plus a kaon was also not studied experimentally. And this was pointed out by these authors here. So given these motivations, what kind of signals we can expect in our parameter space? So this figure is just resuming, summing up what I just told you. So we have these two different kinematic regions we study depend on the mass of the A2. So in one, the A2 has this decay into the lightest singlet. In the other one, we assume that this is the dominant decay mode. And then you have all these signatures of a bottom meson decay that you can explore. And of course, above these lines, you don't have enough masses to, or the masses are too large of these scalar particles to allow for these B decays. So given that, how can we actually experimentally try to prove these signals? And to answer this question again, first we have to look for backgrounds. And if you consider the 4 muons case first, then there is this dominant background of the production of a J psi and phi resonances, each decaying to a pair of muons, which is relatively large because we are trying to probe branching ratios, which are really small. And in the 4 muons analysis by the LHCb, this is removed basically by vetoing all pairs of a positively charged muons, which lie in these intervals, which are where really these standard model resonances peak. Okay, and after that, the analysis becomes essentially background free. So if this is so for the 4 muons case, if we do the same cut, we are sure that the 6 muons analysis is identically background free. And this means we can just obtain the bounds on this process for the branching ratio by normalizing in regard to the 4 muons case. If we repeat the same analysis and just scale up the different efficiencies that we will get. So here is how we actually do it. We also include this factor to take into account the larger production cross-section from 8 TeV to 14 TeV or 13. And we can also scale by the different luminosities at which we want to obtain our prospects on the maximum branching ratio. So so to get these efficiencies, we need to repeat basically the same analysis that was done for the 4 muons case. Let me show you what are the basic and most important selection cuts in this analysis. So first, they require that the leading muon in the event has a transverse momentum above 1.7 GeV. And we have to require the same to simulate the same hardware trigger that was used at 8 TeV. Then for the reconstruction of the tracks, it is required that each one has a transverse momentum above 500 MeV and lies in this pseudo-repetitive volume. And finally, to guarantee a positive identification of the muons with an efficiency close to 100%, it is required that each muon has a total momentum above 2.5 GeV. And these first two cuts really show how we get much smaller efficiencies in the 6 muons case as expected. So here I'm showing you some normalized distributions to show the effect of these cuts. So here we see in the distributions, we want to study the case of the maximum momentum PT of the muon. And we see that indeed, because we have a larger multiplicity of particles, each muon in the event will have smaller energies. So it's likely that no one can surpass this threshold, which is really what we see here, that really these 6 muons distributions are peaking in a region which we cannot get. And although this hardware trigger is expected to be removed with the upgrade of the detector, we still have to worry about the second one, although we can require a smaller threshold. And for the same reason, we also expect, we also lose a lot of events by requiring this minimum PT. So showing you some numbers, what we have. So in the 4 muons case, the efficiency is around 0.1, more or less independent of the mass. And in the case with 6 muons, we have an order of magnitude smaller efficiencies. And we get, of course, even smaller efficiencies in the case of the decay with the kaon, because we have an extra track to which the initial energy needs to be shared with. So it can come as a surprise that actually our limits in this last case can be stronger than in this case in which we don't require the presence of the kaon, but this can be explained by the fact that the production cross-section of a B+ is actually larger than the production cross-section of this meson here, which compensates the smaller efficiency. So this is really an additional motivation to search for these decay modes, on top of the theoretical observation that this is really the only mode you can probe when the two scalars are degenerate in mass. So I also here plug in the number that they get in the study with the 4 muons. Of course, the limits are a bit stronger as expected, but not much stronger than what we obtained. So next, to conclude, I'm just plotting some of these limits in comparison to what we expect from other data. Before that, maybe I can ask if there are additional questions or not regarding the analysis itself.
Well, maybe you will answer to that now, but I was wondering, like, which of these fit better with the current, anomalies, for example. Like, is there any favorite mode in terms of the anomalies, or any, for instance, with respect to the relation between the masses of the A1 and A2, for example? Is there any preference for one mode or the other?
Yeah. So what really is important for the B anomalies case is the relation between the mass of this vector and its coupling to quarks. So the preferential mode, if you want, is just what can constrain more, I would say. But then I will also mention the case of the G-2 in a moment.
Okay.
So here, this is exactly what we aim to show, the maximum mass of the vector we can probe with this analysis versus the coupling to quarks. Here, the solid lines are for an assumed luminosity of 3 femtobarns, although now LHCb can achieve larger luminosities. And here, the lines, the dashed lines are for upright 2, so assuming a luminosity 100 times larger. So here, regarding your question, we are showing the relation, the specific relation, such that this vector can explain these RK and RK star anomalies. And superimposed are these bounds from meson mixing I told you about in the beginning. So you see that first we can outperform these bounds, which is a really important thing to have because, of course, they depend on different parameters. And even if the recent results from the recent results on this delta MS are confirmed, this analysis can still be competitive. And furthermore, they can probe this space here, which is still left untested, under which this vector can really explain the anomalies. So really by doing any of this search, we can do that. But for some choices of the parameter space, really the B to K transition is the most promising. Here I'm showing you another plot, maybe a bit messier, but here we are just showing you in the plane of the masses which kind of values we can probe, and we use the same notation. So the solid lines enclose the region which could be probed with the current luminosities, and actually a bit smaller luminosities than we have now, because these are the limit for 3 femtobarn of data. And then in the dashed lines is the region which could be probed by these 300 femtobarns of luminosity. So you see that indeed in the future, we could expect to probe basically the entire interesting parameter space. And the reason why right now we basically can only probe this region here is that in this one, in this case of the 2-body decay width of A1, A2, that then goes to 6 muons, here in this region, we get close to the degenerate line where these particles have the same mass, where our signal in the case of the 2-body decay is much smaller, and the limits we obtain are actually a bit weaker also in this region. And note that following the same strategy that was done with the 4 muons case, we cannot actually probe this benchmark around 1 GeV of the lightest particle, because we're doing this veto on the resonances of the invariant masses of muons to remove the background. And I would also like to point out concerning our motivation that this is actually an important benchmark to consider, as it was pointed out in this paper here, in which they consider not 2 scalars but just 1. And in that case, provided this scalar is CP even, then this is the most likely configuration which could explain the G-2 at 2 sigmas for natural assumptions of the composite parameters. So it's actually important to try to probe this benchmark, and we cannot do it with the current analysis. But what they also point out is that slight modifications could allow us to prove this point. If instead of doing these vetoes on these mass intervals, we instead require that the 2 pairs of muons reconstruct the same particle, because that's what happens in our signal and not in the standard model case. And if we instead do that, then we can expectedly get the same efficiencies and then the same limits on the branching ratio while probing this shaded region here.
But can you get, like, because I guess this 1 GeV veto is because of the phi, no?
Yeah.
Can you get V2 phi? Because
that background, you mean?
Yeah, like V2 phi with both phi's going to near.
Yeah, you can, but they also discuss in that analysis that in that case, I think the background is even more suppressed than the background I showed you before. So the branching ratios are much orders of magnitude smaller.
Yeah, they should be very small. Yeah, because the branching ratio of phi to muons is like 10 to the minus 5. So then you have 2 is 10 to the minus 10.
Yeah, I think that
it depends on which branching ratio you want to probe.
Yeah, I just mean for the cases we are targeting around this 10 to minus 8, 10 to minus 9, this should not be a problem. But of course, this is just a loose argument, but slight modifications could be done, I guess, to probe this point. I just wanted to mention it because it's really just a point, but it's interesting regarding these anomalies.
What's the reason not considering the regular V0? Because you're considering the charge B, but not in the VS, but not the regular V0. There is no room for branching function. What's the reason?
The B0.
Yeah,
I will mention that in the conclusions. The analysis would be like the arguments would be entirely the same. You could do that, and we get some numbers. I get some numbers for that.
Yeah, because you said that the production of B plus is larger than that of BS, but maybe
B0 is also is also larger.
Right?
Yeah, so the limits are even better in that case. But the analysis would follow in exactly the same way. So I was just showing you one case.
Okay.
And you would probably lose the argument about the into SLL anomaly.
So we will report these numbers to study instead DD transitions. But if you take the anomalies into account itself, I don't know if you can prove this V to an S.
And then there's another very important argument, and is that if you can do it with V0, then Bell and Logan can do it, which is not good for us.
Yeah, I wasn't sure I was asking the question because I was thinking that some reason of that nature would appear, and I would...
Yeah, that I didn't know. But yeah, finally, I would also like to mention that indeed, if a signal was observed, it would be very straightforward to really try to reconstruct these scalar particles. And here is one example for the case in which the A2 can decay into two A1s. So you can just take into consideration, try to calculate this delta function, which basically computes all combinations of a positively charged muons, which can reconstruct our A1 particle. So there are three possible combinations, and you just choose the one that minimizes this delta function, and then you can reconstruct your A1 particle. As you see here, you get a narrow resonance following this algorithm. And then for the A2 particle, we can just choose the A1 candidates we found, which are closest in delta R in angular separation. And this is a simpler example that shows that we can get narrow resonances, even though we don't actually need it because the resolution is so good. But this is just an example. And finally, last slide, again, unless there are questions, I would like just to comment also with, make a comment regarding the complementarity with other LHC searches. Because this vector, again, like I told you in the beginning, they can be produced on shell IPP collisions if it's not supermassive. And then you can search for it decaying into these two scalars themselves. Here we are also assuming larger masses for the scalar just for purpose of generality. So here we also recasted this multi-leptonic search presented by the Atlas collaborations, which is sensitive for the to the case in which the A1 can couple more to taus or to muons, although we were focused on the second case for the anomalies. And it is interesting to note, so here the dashed lines are show what we can probe with the higher luminosity phase of the LHC. And it's interesting to note that indeed this parameter space, which is interested for our low energy signature, is left completely unprobed for two reasons. So in the case of taus, if these light scalars have a mass below 4 GeV, they basically cannot decay. And in the case of muons, because all these leptons come from a very heavy resonance, in the case of muons, the muons you'll get will be very, very collimated. So the current strategy cannot cover such small cones between them to disintegrate them. So this region is completely left unprobed. And here is because they do a veto on the zipple mass to get rid of the standard model background. And again, slight modifications, if you are able to solve smaller angular separations between the muons, or instead of requiring this veto, you just gather the effective mass of the total leptons in the final state and require that it peaks a large momenta, then you can also remove the background while probing these white spaces. So that would be the goal, to try to motivate these kind of slight modifications. So indeed, I don't know how is the time, but perfect, yeah. Okay. But these would be the conclusions. So I tried to argue that given that we have found really no big deviation from the standard model, we should really consider exploring it in radically new and unexplored regions of the parameter space. And this cannot be random. So we do have to try to find some motivation in rich frameworks, which is the case of composite Higgs models, which for instance predict these heavy light coupling to arise. And this scenario can trigger rare B decays into multiple muons. So here are the cases I discussed following the analysis strategy that was pursued by the LHCP for the 4 muons case. And I show you that we can probe branching ratios as small as 10 to -9. And there are modifications happening in the detectors. So maybe we can probe even larger branching ratios. Regarding your question, we also study the case of a B0, which has a larger production cross-section. So the limit in this case is more stringent. Again, even also in this case, the two-body decay width vanishes in the limit of the generate scalars that give rise to the 6 muons. So you have to prove some B to K-on interaction. In the case of this K-on star, we have to consider a decay mode for this particle because it's unstable, and we focus on the case in which it decays into a charge K-on and a pion. And then, of course, our efficiencies are penalized by the branching ratio. So here the limit is not that stronger. And this is important in this case to probe not a B to S transition, but a B to D transition. None of these signals we show that has been explored experimentally. I do hope that they are in the very near future, especially this case here with the K-on, because it's really a key signature, not only because it can offer the best limits, but also because it's the only one which can probe these limits where the masses are equal. And to conclude, I also wanted to mention that this process are also important to constrain these standard model effective field theory approaches I was telling you in the beginning. Although I don't know any studies in this regard, these kind of transitions between mesons can probe for fermion operators, which in the case that you include these light scalars, you also probe these, for instance, dimension 8 operators with singlet particles here. And these kind of standard model effective field theory approaches, including other degrees of freedom, have been and are currently under construction, especially for these kind of axion-like particles, because they are very compelling, first theoretically, and also to be detected nearby us, because they would easily escape the searches we have done so far. So these kind of bases are currently under construction and are very interesting for us. Okay, so yeah, thank you.
Thank you, Maria.